Hey everyone, welcome to another hardwear.io webinar. We all attend a lot of conferences and trade shows in the past to learn, interact, and grow our business network. With the current situation, many of us have not been able to network with a lot of industry people. And saying this, we were wondering at hardwear.io, how can we make this happen for our hardware researchers to connect with various like-minded people from the industry? We came up with an idea called Fix Up, where based on your professional interest and requirements, we would match you with another registered attendee of our upcoming hardwear.io conference. So those who are interested to grow your social network with hardware hackers, researchers, please do sign up for our Fix Up session. I will be sending across the link later in the Zoom chat. To make a successful side channel analysis on SoC device, we need to overcome various technical issues like tuning the social device measurement, optimal location of the surface of the die, and the right attack to extract the secret key. For the very same reason, we invited Hugues Thiebeauld, who's the founder of eShard company based out of France. He has vast experience in cryptographic side channel or fault injection techniques for security evaluation of banking, e-government, and telecom products. For those who are new to hardwear.io webinar, the format for today's session would be Hugues will present his webinar. And if you have any questions, please send it across via the Zoom chat. We would answer them after the presentation is complete. So without any further delay, let's welcome Hugues to begin his presentation. Hugues, you can start.
Okay, so let me share my screen. Okay, I hope you can see my screen now.
Absolutely.
Okay, so good evening, good morning, good afternoon to everyone from wherever you are. So my name is Hugues. Thank you for the intro, Andrich. And indeed, I'm going to talk to you about different works we have been conducting in the past month and years, and all targeting such an analysis on SoC devices, or SoC standing for System on Chips. And we want to show that from a practical point of view, how many challenges you can face, because you will face these challenges if you do it by yourself, and how on our side we tackle them. Okay, so in order to illustrate the different use case, we used different SoC. So this is kind of an overview of different experiences we have been accumulated over the past years. Okay, so it looks like a Graal request. So let's see why. First, I would like to do a very brief introduction about sidechain. I'm pretty sure that most of you know about it, but I think it's quite an important exercise to make it super simple. So what is a sidechain analysis? First, the sidechain analysis, you have typically a device. It's a hardware device. Here on the left, you have an FPGA device, and you have a key. The key is secret. Okay, this is the Graal. You want to get it. How can you get it? The algorithm using the key has been designed to be resistant to all kinds of logical attacks. But it has not been designed to be resistant if you can get, or if you can monitor the intermediate values along the algorithm execution. So what we are doing is we are leveraging the fact that the algorithm is being executed on a hardware device. And from this physical execution, we want to grab pieces of information related, this information being related to these intermediate values of the algorithm. Okay, so the different ways to measure could be the power fluctuation, electromagnetic near-field electromagnetic monitoring, but you can find some other tips like using a laser for optical analysis, typically. At the end, you have data. These data are supposed to represent your physical execution of the algorithm. So here on the right, it's an AES, and you have 10 or 11 here, sorry, specific rounds, and you can see the different cycles. If you apply this same execution using the same key a lot of time, you will have a lot of traces. And from these traces, you will apply some signal processing and statistical processing in order to retrieve the secret key. These statistical tools all aim at doing the same thing. It's all the physical representation of the traces. Only one key can explain them. This is why you try to extract, right? So let's see what it gives in practice, because the attack is practical. You can apply successfully such an, and it's not that difficult. On a non-protected device, it can even be very fast. Actually, you only need a few minutes to manage a key extraction on some devices easy to attack. Okay, so that's important to take this into account when you design a product, when you select a technology, and regardless if you do encryption, authentication, integrity, or authenticity verification, that's necessary to think about this potential threat. So now what about this threat on SoC? Here, I give an example on a device. So this device is typically used in mobile phones. Okay, so looking at this device, here you have a backside image. Okay, so we made a high resolution imaging from the backside, and you can see that actually it's big. Here, this one is not the biggest one we know, but only that one is 8 millimeter per 9 millimeter. So it's not far from 1 centimeter square. So when you look at it carefully, you can see that there are a lot of things into it. But these lot of things, or patterns, or areas, the difficulty is to know where is your area of interest. What are the different gates you would like to target in order to make a proper measurement? Because if you try to do a power fluctuations of the whole device, it's on the SoC, it's very unlikely to succeed if you want to target an AES, an integrated AES. So it's an hardware execution is super fast, and the signal is very low compared to the whole signal created by the SoC. So you want to be, you want to locate to locate where you will do your measurements, and for that purpose, it's much better to do a near-field electromagnetic attack. So to use an EM probe. Okay, great, but where to put your EM probe? Again, back to my square one. It's difficult because you have a lot of different areas. So you can guess which areas are where. Here I can see that this is a 4-cores device. There are 4 cores, 1, 2, 3, 4 here in the center. But I don't know where. I have no idea where is integrated AES. And if we look more deeply into the potential here, you can see that it's not the latest technology. We are talking about 32 nanometers, but it has 3 million gates per square millimeter. So in total, you have 168 millions of gates approx on this kind of device, on this device. What does that mean? That means that if you are looking for an AES integrated AES, if you look at Mr. Axel Poschmann publication, it's in the ballpark range of between 5 to 15 kilogates equivalent. So we are talking approximately about 0.01% of the whole surface that represents my area of interest. Wow, that's very small, right? So if we try to put that together with typical EM probe that people use in our industry. So Langer is doing very good product. It's not the only one provider, but this one is a typical one. And if you look at the different resolution of classical probes used by the people in the industry, so I use different examples here. So one is I would say a cheap one, the RFB probe is the one on the left. The resolution is approximately 1 square millimeter. So 1 square millimeter is my square, my gray square here in the middle here. I try to represent what is 1 millimeter, okay? Because in comparison, if you take another probe like ICR, much more accurate in terms of location, of resolution, sorry. One is 500 square micrometer, which would represent only the orange part. And if you take, sorry, the smallest resolution, the 150 square micrometer, you will target only the blue square. So you can see the big difference, right? It's important to have this kind of visual comparison to see the resolution. Now let's see. If I take my Axel Postman's example reference, with a longer probe, the pen probe, the one on the left, on the chip, my 30 nanometer chip above, I can capture 2.35 millions of gates. If I take the one with resolution 500, I can capture 0.59. And the smallest resolution, I can capture 53 kilogates, which is not far from the size of my integrated AES, right? So it's not too bad. Okay, now if I take the latest technology from TSMC, so 5 nanometers, what does it give? So here I will talk in transistors, sorry, not in gates. So I put two examples. The biggest probe, you will capture 135 millions of transistors. And if I take the smallest one, I will capture 3 millions of transistors. So it's a challenge, right? So the good news is the transistor of my AES processor or integrated AES will give signals, interesting signal on a surface bigger than just the surface of the corresponding gates, okay? So you will have leakage around. Great, but that's still a small piece. It's still a small piece of the die, right? And like this, I am unable to tell you where it is. Maybe you can have a very advanced reverse engineering or delayering techniques to get it, but that's not obvious. So you need, unless you are an expert, you need to find some other tricks. First trick I would like to share, and you can see the whole details in the Ash's paper from last year. My colleague made this talk, Aurélien Vassel. They use the trick of an infrared thermal analysis. So basically, what they did, and they captured the thermal activity, okay, for when they did a lot of AES and when there was no AES, and they tried to compare together, right? It's a comparison effect. So you have approximately the picture on the right, where you can see the hotspot maybe here at the bottom in the glue logic. Still a big area, right? So maybe it's not good enough in order to find precisely. So in order to get to the next level, my suggestion is to do a cartography. So what is a cartography? I would like to show you an example on another chip. Here we go. So this one, it's a recent SoC we have been analyzing. And you can see that here we made the cartography on the given square here, orange. Okay, So we can zoom on this. Okay. And on each point, we acquired a few thousands of traces. So each trace is one execution. And we try to apply some statistical tools for each individual point. Okay. After that, we represent the corresponding heat map on this tool. And you can see that the brightest point is the S and R is the bigger. Okay, so the brighter is the SNR the bigger. So I can click on different points. If I go here on the left where it's not that bright, you can see that for each individual point, I put the raw signal on the top left, the average signal on the top right, the t-test on the bottom left, and the average of no AES on the right. Because you don't want to have a false positive, right? So this is why you always keep some execution where there is no AES, and you don't want to avoid any false positive. Cool. So here the t-test is so, and if I go to the brightest parts of my scan and my heat map, you can see the t-test is very interesting. Okay, you can see a clear signal here. Looking at the raw signal, it's disappointing. It's not that beautiful. So you can see that this one is quite challenging from a signal point of view. And on the right, you can see that average signal is pretty good. Okay, so there is some hope if you put your probe here. And when you define where to put your probe, you can do a multi-millions acquisition. So you need to capture a lot of traces usually to have a proper analysis. Sometimes you don't need it, but I would say the ballpark figures of millions of acquisition is nowadays the norm. Okay, cool. So now I know where to put my probe. So I will capture a lot of acquisition. There is a second thing you need to take into account is a proper way to trigger your signal. So this one can be challenging, more or less challenging. Okay, I will talk about how you can insert code afterwards in the device. But on this example, we were lucky on the given example here. So you can see multiple decryption here in blue on the top. You can see that we could trigger because the signal was big enough on that example. Most of the time it's not the case. Okay, you will need to find another way to trigger. So when you have a lot of successive encryption or decryption, it's more convenient because you can see where you have multiple execution on the same satchel trace. Okay. However, having said that, when you are not in control of the plain text or the ciphertext that you are about to encrypt or decrypt, that could be more challenging because you need to make sure that the first plain text, you know exactly where is the first execution and so on. If you miss the point, okay, you have a shift between your measurement and the logical value, and you can miss the attack. Okay, I found that interesting to show that example because on the SoC everything goes super fast. It's a piece of it's hardware accelerated. So on that example, one single execution of one AES was 11 cycles, which means 55 nanoseconds. So it's important to get the proper measurement in order to not miss this kind of signal, right? So you need the proper sampling rate and the proper frequency in order to succeed in the analysis and avoid missing the interesting information. Okay. After that, you will find a lot of different cases. They are all different. On that particular one, the hardware is built in such a way that you have 4 executions systematically done, which allows for a sequence of 4 execution for performance reason, but that's very much related to this specific design. And you will see another design if you do another SoC analysis. So second challenge, be careful to not miss the point because it goes fast. Okay, so your setup must be good. Third challenge is everything around the execution. A SoC is not a simple product. You have a lot of concurrent executions. So a lot of potential noise that can overwhelm your analysis. Okay? Even so, your probe is more or less well located on the surface of the die. Very soon you can be overwhelmed by all these different activities that can that generate signal as well. So here I wanted to show that it's just purely an example, that one, even so it doesn't apply very much to integrated AES, but I found that interesting to show that only the governor on Android, you can tune the governor to have different, I would say, execution strategy. And here you can have on-demand, provide power or a clock on demand, or only target performance. And you can see that if this is on demand, when we do a lot of successive decryption, on the left, the nature of the signal drops because actually the different resources available at the chip will just adjust accordingly. However, if you choose the performance, you will have a kind of regular signal. Okay, I found that interesting to share that. A second one is actually when you are targeting a sat channel and this is going to a specific core, it could be a software. That's quite interesting to be aware that depending on which core you will target, you will have a different quality of signal. And again, you want to be in the best condition to do your analysis, right? So here we made this analysis. It was on a SoC with 8 cores. Okay, so you can see the picture for the 8 cores. On the top, it's just the cartography with AES running on each core. And at the bottom, we made like a diff. This was a diff between the activity with AES and an activity and the activity with the other core without AES execution, in order to have I would say, a stronger metric. Here you can see that when I send the execution on the core 0, and if I observe this one, I will have a clear hotspot. Okay, so the quality of the signal seems to be stronger. But if I send it to the core 1, that's not that great. And it's exactly the same code that we send to the core 0 or we send to the core 1. So from a strategic point of view, as you can see, it's much better to target the core 0 than targeting the core 1. First. Second, it's quite interesting to see as well that when you send something to the core 0, you have still an activity around the core 1. It's likely a bit bright here. You can see it. Okay, so they are like cross-correlated. And sometimes per cluster. Here we wanted to show that it's clustered, and the core 0, 1, 2, 3 are clustered together, and 4, 5, 6, 7 as well. Okay. Okay, so some here key thoughts, some thoughts that I would like to share with you. It's be careful with adjacent activity. Sometimes you can have fetch in the DRAM that can affect seriously the quality of your signal. So try to be in the best condition. If you can, try to be in the best condition to make your analysis at the beginning. It does not mean that at the end you won't be able to attack with a normal execution with everything on top of it, but start by being in the best condition. And being in the best condition, sometimes you have to be in the bare metal, if you can, it's better, and to have privileges in order to adjust some hardware features that can be very overwhelming in your signal. Okay, I'm talking about the right selection of the clock, adjusting the cache mechanism. It can be very noisy or not, or depending of the SoC. So you have to manage all these hardware features. Okay, this is your challenge number 3. At the end, this is maybe one of the most challenging between you and I. Number 4. Well, okay, you have good quality of signal, you remove the noise, you are in the best condition, but can you get the key? That's always a question. So here I'm taking an example that we had recently. So I wanted to show that you will need to think as well your search change strategy. So what do I mean by that? Here on that example, let me just do a bit of clean. Oh, okay, I try to show that selection function. You know, this is a piece of intermediate data that you are targeting. Here, if you try on that given example, classical selection function like the output of the S-box, or another one, it can be the add key, typically. You may not find easily the leakage because your selection function must match the leakage of the device. It looks obvious like this, but sometimes you can have surprises. So this is why it's important to do t-tests in order to see if there are potential first-order leakages. Okay. Here on that example, we didn't manage to break it with, I would say, straightforward selection function. So we had to go one step ahead, and we understood by trying different search analysis, we understood that actually the leakage model on that specific case, it's a delta, but not where we expected it. So it's a delta between the end of the round, let's say here 10, and the end of the round 9. Actually, or in decryption, it's beginning, it's just after the first add one key, XOR just after the second add one key. So you need to make the delta. The delta, I would say, you can tell me, but we don't know K9 and K10, so we cannot do the attack. But think that K9 is for me just a constant value, and I'm targeting K10. So if I think like this, I can do monobit attacks. If by doing monobit attack, you can circumvent this issue. So it's what I made here, and you can see that on that particular use case, here we have the byte 0, byte 1, and in blue it's the candidate is the proper one. So on the left, you have the outcome of a monobit, and we gather together the different pieces of attack from the monobit. And on the right, you have the convergence traces, so number of traces versus the factor. Okay, so you can see that clearly my best candidate C1 is on top for a while, and I can clearly say that this is the one for the byte 1, 2, and you have a very good leakage for all of them. You have a way to make it even better, because it's a monobit, you can say, okay, you can read this paper from Shan and al, and you will see that a linear regression analysis may very well apply to this use case. So this is what I made for you. And indeed, this attack is even better. We can break the whole secret on this given example very quickly. Okay, as you can see, the results are very good and very neat. Okay, doing that, I can find the whole secret because it's C9, 99, and so on. The whole key is there. Okay. So at the end here, I can show that we managed to get the Graal. So let's go back to my presentation, and it will be my main conclusion. Classically, attacking, doing a side channel, a practical side channel on a SoC is, I would say, very seldomly quick and easy in identification. So finding the recipe is not easy. You have to tackle a lot of different challenges. And this may take, if you're an expert, it may take weeks to find. And when I say weeks, it's more 3, 4, or 6 weeks than 1 or 2. Okay? And you will most of the time need a multiple expertise. Okay, not only a side channel expertise, but you will need some embedded software expertise. Okay, because at the end, different techniques must be developed most of the time in order to find your way. But once you have the recipe, it's quite interesting to see that the exploitation is not necessarily a big deal, actually. When I know where to put my probe, where I know how to disable all these hardware features that overwhelms the signal, that makes the signal very noisy, you can manage to make an attack in, I would say, a few hours sometimes, and with a relatively simple equipment. Okay, this remark is excluding the fact that sample preparation may be necessary. So I am excluding the fact that on some SoC device, you may need to manage the issue of the package-to-package device, the package-to-package technology, sorry, where you don't have an easy access to the dice so easily. So it may be a challenge, and this challenge, you will have it in identification and exploitation. So I was given 30 minutes, so I will need to stop at this point. I can speak hours about it. If you want to know more and talk and ask us further question or discuss about the sexual topic, this is a chess conference this year, and this is online. So we created this virtual booth. And feel free to, this week we are very much committed to make demonstration, or we can even afford people to do remote side channel, where from wherever you are, you just have to book a bench, and you can make an analysis, drive an oscilloscope, drive an XY stage, and make your own analysis all remotely. Thank you for your attention.
Thank you, Hugues. Audience, if you have any questions, this is the time you send it across via the Zoom chat. We have received some questions. Let me read them out for you. The first question is, it's about the paper. Can you share the link of the paper? I believe this was one of the papers you were referring to of Axel Poschmann.
Axel Poschmann, if this is Axel Poschmann, I think I put the reference. I think you can simply take this one. If you type such an resistant crypto for less than 2,300 gate equivalent, find it, or you should contact me, and we'll manage to give the proper reference.
All right. what are the tools, methods used for infrared thermal analysis?
So here, actually, you need to have a setup. So I was not the one doing this, so maybe I will remain generic and you will have to go back to us if you want more information. But we made this analysis. They were able to capture actually the thermal activity, roughly speaking, on the whole device. So it was not targeting a specific part, okay? And the main challenge was to make sure to make some operation to the SoC. So like AES, no AES, AES, no AES, kind of, I would say, cycles of execution, non-execution, in order to have enough granularity in the execution and manage something that is particularly changing with when something becomes hot, the inertia is very slow, okay? So in order to avoid the false positives, they had to find tricks for this. So you have information as well in Ash's paper from Aurélien. He was the one doing the analysis, this one particularly.
All right. Can you please elaborate the relationship between the probe size and the signal availability? That is a bit confusing. So
this is confusing, but I think this is a very difficult topic. When I gave the resolution compared to the number of gates, okay, this was to give a point of reference. But you are absolutely right, thinking that actually the activity can be monitored in a wider area. But this one is highly dependent on the chip layout and the chip technology. So usually speaking, this is just by an empiric way that you will find the proper signal. And this is highly dependent from one device to the other.
There is another question. Do you recommend any tool software for beginners to assess the trace and find key by using power analysis or EM analysis?
So that depends what you mean by tools. From a hardware perspective, from a hardware equipment, you will need mostly one oscilloscope. Okay, you can even take a simple oscilloscope, a cheap one like a picoscope, and you can do first analysis. You will face very quickly that this equipment is limited because you need to go relatively high in power, right? And you will need to investigate. From a software point of view, you have different open source. At eShard, we created the scared open source project. So you can go on GitHub and look for scared. You will find a toolbox where you can apply, I would say, data management and data processing with such channel. So you will be able to do proper such channel. Okay. After that, our experience shows that if you want to do it seriously and in depth, you will need to invest at some point in hardware and software.
I think what you could also do is book a bench with eShard for during the chess to explore more.
Exact.
Right. We have a few more questions, but I'll just take two more. Did you try DL attack? And I think it should be more efficient compared to CPA.
DL attack, the problem is it's efficient. Usually you do a profile attack, right? So here we wanted to do a non-profile attack. So what does that mean? For those who are not familiar with this profile or non-profile. Deep learning, you need a learning phase where you know the key and you have access to this information and you can very much train your network according to some knowledge you have. After that, you will try to exploit it on a secret, on a unknown key, okay, on a secret key. Here, we wanted to show that we can extract the key on non-profile attack. So you can still do deep learning on non-profile. Actually, it's one guy of my team, Benjamin Timon, who wrote the first paper about it. But that's very that needs a lot of computation, because you need to learn, you need to to create a lot of model. So that's too intensive. So classical techniques like the one I shared are much more efficient actually. So this explains why we decided to do that. But my last point is, when you do a comparison in exploitation, think about it. One, what was the cost of doing a training? Most of the time people tend to forget about it. And second, this kind of analysis, you have to think about one thing, just do that on cross-device. If you want to have a fair comparison, never do your training on the same device as the one you will use for the exploitation.
All right. One last question. Why there are 4 AES patents?
I try to explain that during the talk. It's a good question. This one is very much related to this specific SoC. This is a decision of the designer to make a very fast, to have a very fast AES engine in order to decrypt or encrypt very large file. You can do 4 AES in a row. And this is how you can leverage this specific hardware. But it's completely, it's specific to this device.
All right. Thank you so much, Hugues, for this interactive webinar today. I mean, we had a lot of questions from the audience as well. And thank you so much once again. I hope you have a good time, and some of our attendees also book a bench with you during the upcoming chess session.
Thank you to all of you.
Thank you, everybody else. We have our upcoming webinar scheduled on the 18th of this month. Please do join in, and also do check out our upcoming conference, which is scheduled on the 1st and 2nd of October. We have some really cool new research which has not been presented before in the hardware security space. So stay tuned and stay safe, everybody. Bye.